Hi, students. I hope you are having a wonderful first week. I just wanted to go over a few things from the first set of material. Sections 2122 and 23 are due this week. This is not going to be a lecture. Your lecture material is in my lab. I just wanted to introduce a few problems that you'll see on the homeworks and quizzes. Go over the concepts for them, and I'll mention some of the lecture type material as we get through the problems as they come up. But otherwise, just email me if you have questions about anything we're working on. I know some of you had some trouble with registering from my lab. I sent you some emails yesterday about that. If you're still having trouble, please let me know. I'm here to help. I want to make sure you get started and are able to get into the material as soon as possible. But for now, let's talk about some of the problems in sections 2.1 through 2.3. So first of all, what does it mean for a set to be well-defined? A well-defined set means I can determine without question what is a member of the set. So for example, if I look at the set of most interesting movies in 2021, what I think is an interesting movie might be very different from what you think is an interesting movie. So my set of interesting movies might vary from your set. So this is not well defined because the definition may vary from person to person. So it's not clear what belongs in the set and what does not. However, if I look at the set of Academy Award winners, there's only one person that won Best Actor last year. There's only one group that won Best Set Design last year. It's definitive. So this is a well-defined set. Now, I want to express in roster form the set of, not moths, oh my goodness, my typing, that should be months, whose names begin with the letter J. So let's fix that right there. This is months. Okay, so to denote a set, I need to do curly brackets. The elements go inside the curly brackets. So what months begin with the letter J? Well, that would be January, June, and July. And I think that's all of our months that begin with the letter J. So there is my complete set. Again, make sure that you're using the curly brackets to denote a set. I want to express in set builder notation. Okay, now for set builder notation, we're going to begin the same way. This is curly brackets to define the set. But inside, I use a variable to represent the elements of the set. And then I'm going to define a rule so that you know what can take the place of the variable. So the way we begin the rule is always with the word such that. So it's going to be the element, the set that consisting of elements X, such that is the vertical line. That's how we read that, such that. X is an element of, so we use that symbol for is an element of. And then notice these are counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's our set of natural numbers. So I'm going to use the script in to denote the set of natural numbers. But the set of natural numbers keeps going. It would include 10, 11, 12, 13, 14. I don't want to. So there are two ways that I can represent that. I can say, and X is less than or equal to 9. So my natural numbers less than or equal to 9 are 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. Or an alternate way that I could do that, if I didn't want to do the less than or equal to, I could have replaced this part with X is strictly less than 10. Those are equivalent statements for natural numbers. When I'm talking about those counting numbers, less than or equal to 9 includes 9. Strictly less than 10 does not include 10. So they're absolutely equivalent. When would those two not be equivalent? if I allow like decimal points. 9.9 is not less than or equal to 9, but it is strictly less than 10. But I don't include decimal points in natural numbers, so it's not an issue here. So I could write it either way. Now, let's introduce one other concept as long as we're on this slide, the cardinality. If I asked for the cardinality of A, that's asking how many elements are in A. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, the count of objects in there are 9 distinct numbers in 1 through 9. So my cardinality of the set is 9. Okay, let's go to the next example. All right, true or false? The empty set is an element of the set consisting of A, B, C, D. What do you think? False. The empty set is a set. It is not an element. Okay, so it would be a subset, right? A set can be a subset. That's exactly what we're saying right here. The empty set, notice these are both notations for the empty set. The empty set is a subset, the empty set is a subset of the empty set. That's a true statement. Notice again, this is not a strict subset. This has the equal sign on it. So if I'm looking at A, B, C, D, right? The set A, B, C, D is a weak subset, right? Like this, of itself. That would be a true statement. Okay, so for the sets, U, that's my universe that we're dealing with for this problem. So the whole universe for this problem consists of A, B, C, D, E, and F. I want to construct a Venn diagram. So we're going to draw, I drew the wrong thing. There we go, a box. And this box is my universe, U. So all of the elements, A, B, C, D, E, and F will be inside there. Now, I want to write them so that A and C are inside set A. So if we call this set A, it should have the elements A and C. And B, E, and F are inside set B. So if this is B, E, B, and F are all in here. And let's see what else we're missing from our universe. A, B, C, D is missing, so it's out here in the universe. E, and F. Okay, so that's what my Venn diagram would look like. Notice that if A and B had something in common, they would overlap and include that element in both. All right, so now we want to describe the following sets. U is the set of furniture stores. Okay, so that's my universe. That's everything I'm dealing with is a set of furniture stores. A is the set of furniture stores that sell mattresses. B is the set of furniture stores that sell outdoor furniture. And C is the set of furniture stores selling leather furniture. So A intercept B is the set of furniture stores that are in common to both A and B. That's what the intersection. Intersection is an and. And means it belongs to both. Okay. So for us, that would be the set of furniture stores that sell mattresses and sell outdoor furniture. They have to do both. I have to be able to walk into that furniture store and buy both a mattress and an outdoor furniture piece. That's what's in the intersection set. Now let's look at this. This is the complement. The complement means it's not in the set. So if A is the set of furniture stores that sell mattresses, then the complement would be the set of furniture stores that do not sell mattresses. Okay, Now, let's also look at this right here. This is the union symbol. This is the intersection. Intersection was an and. Union means or. So instead of an and, it's an or. What's the difference mathematically between and or? Or in math doesn't quite mean the same thing that it does in English. In English, when I say or, it kind of means like one or the other, usually, but a mathematical or means it's in one or the other, or maybe both. It just has to be somewhere, okay? So let's put this together now. My set here is going to be the set of furniture stores that, because it's a complement, does not sell. All right, the complement of selling mattresses is not selling mattresses. Or because this is a union, not an intersection. And then we have the complement of C, so they don't sell leather furnitures. Okay, what does that mean? That means when I walk into this furniture store, any furniture store that's in this set, A complement, union, C complement, either I'm not going to be able to buy a mattress, or I'm not going to be able to buy a piece of leather furniture, or I can't buy either. That's what belongs in that set. Let's look at the next example. All right, I want to work this problem. So let's see here. We're going to scroll down to number 32. There we go. All right, use the Venn diagram to list the elements of the set in roster form. Okay, the set is A complement right here, A complement. Okay, so that's the elements that are not in A. What's in A? 11, 14, 13, 17. So not in A would be 12, 15, 16, 18, and 19. Let's do another one. What if I had wanted a union B? That would be the set of elements. So we're going to draw curly brackets. The set of elements that are in A or in B or in both. All right, that looks like 11, 12, 13, 14. 15, 16, and 17. (11, 12, 13, 14, 15, 16, 17). That's it, all of them. Notice that we don't list an element more than once, even if it's in both sets. All right, how about if instead I had wanted A intersect B complement? That's not a very good complement. Let's try that again. Complement. There we go. Okay. Again, we need curly brackets. That means it's in A and not in B. Not in B is everything outside of B. But the only thing that's outside of B, but also in A, is right here, the 11 and the 14. 11 and 14. In the set with curly brackets. Let's try one more. What about A minus B complement? A is everything that's in the circle, in here. B complement is everything that is outside of B. Okay, so if I take the brown and subtract the purple, it removes these two elements over here, the 11 and the 14. So I'm only left with the items in the middle, 13 and 17. 13, 17, curly brackets to make a set. If you're having questions with what I'm doing, please be sure to let me know. Email me. I'll be happy to go into more detail. All right. Now, notice that the easy way to do this was with the Venn diagram. It gives us a visualization. So one way I may start a problem like this is just construct my Venn diagram. All right, so let's stay on the same slide first. Let's try that again. Okay, so we're going to draw a picture here. And this is you, everything in my universe. And set A contains 1, 2, 4, 5, 7. Set B contains 2, 3, 5, 6, 7. So 2 and 5 need to overlap in A and B. So A goes here. B's got to overlap. That's a little bit of a convex circle there for B. That's okay. I'm on a computer. It's hard to draw. All right. 2 and 5 are in common. 2 and 5. So they need to go into the intersection where they're overlapping. Okay. Everything else is in A. 1, 4, 7. And everything else in B. 3, 6. What did I miss? 1, 2, 3, 4, 5, 6, 7, and 8 must be out here in the universe somewhere because it's not neither of the other two. A complement is everything that's not in A. So my A complement here is all this other stuff. Excuse me, outside of A. That would be 3, 6, and 8. So that's a set. Those are curly brackets, and I apologize. I'm hard to draw at this angle. 3, 6, and 8. That's outside of set A, but still in my universe. All right, B complement. What's outside of B? All right, again, curly brackets. Outside of B is 1, 4, 7, and 8. 1, 4, 7, and 8. All right, so the intersection means I'm looking for all numbers that appear in this first set and this second set. Only the number 8 appears in both. So this is the set consisting only of the number 8, curly brackets. All right, let's try A complement. We already wrote that down. A intersect B. A intersect B is what A and B have in common. That's the 2 and the 5. So what am I doing here? I'm doing an or statement. That means it can be anything in here or in here. So by the way, how did I know the order of operations? The parentheses are a grouping symbol. So I always do my parentheses first and then work my way out. Okay. So the or statement means I'm taking all the elements in both sets. So that would be 2, 3, 5, 6, and 8. All right, now A minus B. A minus B. Oh, A complement minus B complement. My bad. Okay, A complement's right here. B complement's right here. So that means the subtraction is all of the elements in this set. We're going to remove elements from this set. Well, I can't remove the 1, the 4, or the 7 because it's not there, but I can remove the 8. So if I take away the 8, that leaves only 3 and 6. So my answer for this guy is the set 3 and 6. All right, guys. Hopefully this gave you a taste of what you're doing in sections 1, 2, 3 for chapter 2. If you have any questions at all, please don't hesitate to reach out to me. I hope you're having a great week. Talk to you again next week.